Yeah, I think it's almost ready. Okay, good afternoon. The slide you see today now is the building damage by a recent earthquake in the north of Thailand, Chiang Rai. It's a moderate earthquake and this building collapsed by that earthquake. So the topics I'm going to explain or speak today, there are two topics. One is about assessment of seismic hazard and risk. It's about earthquake. And another topic about wind effects on building and structure. So these are two different topics. And each of these actually cover many smaller topics and issues. So it is not possible to speak about all these two big topics in a short time. So what I'm going to do is to give you some overview and showing some of our research activities and project activities at AIT that are related to these two topics. Okay, and hope that it will make you understand better about these two topics. Let's start with the earthquake issue. The picture on the right shows the seismic activity in this region, Southeast Asia. So each circle shows the location of one earthquake. There are many different colors of the circle and different sizes of the circle. That depend on the magnitude. So they are varying from small to large earthquakes. The picture on the left showing the tectonic structure in this region, showing that Thailand, Malaysia, Myanmar are all located in one tectonic plate, while India, Australia are on the other tectonic plates. And these two tectonic plates are moving in a different direction. The difference in the movement of this tectonic plate actually is the main cause of earthquakes in this region. And in fact, the differential movement of tectonic plate is the main cause of earthquake around the world. So we can see many earthquakes occur around or close to the tectonic boundaries. For example, this one, we can see a large number of earthquakes occurring around the boundary between these two plates. And also some place close to these two plates because we have many cracks inside the plate, which we call active fault. Okay? These are two earthquakes, a recent earthquake, Nepal earthquake, and Myanmar earthquake. These two major earthquakes also happened close to or at the boundary between the two plates. Okay. And if you look back to about 12 years ago, we had a very large earthquake happen in this region. It's produced by the slipping between the two big plates, the boundary between the two plates, starting from the north tip of Sumatra. And the slipping continued to the Nicobar and Andaman Island, creating a sudden uplift of the seabed along this and trigger tsunami wave propagating to two directions. One approaching Thailand, Malaysia, the others go to India, Sri Lanka, and Maldives, and so on. That's what happened 12 years ago in 2004. It's a picture of tsunami wave that when it's flow onto the land. It's in Kamala Beach in Phuket. Okay? It created a sudden flood with high water velocity. And that's a picture in Phang Nga, southern province of Thailand near Phuket. It showed that the depth of the flooding was about 6 to 7 meters. Around 800 people were killed by this tsunami disaster. It was one of the most devastating disasters in the history of Thailand. And it's also made the people understand or become aware of the earthquake risk or disaster, other type of disaster that can be created by earthquake. Okay, like this one, tsunami. It shows an important characteristic of earthquake disaster. It's low frequency of occurrence, or we call long return period. But although the frequency is low, but it is possible to create a very high impact, like this one. And we may not have it again in the next 100 years. But when it occurs, it will create a large a very high loss and high impact. So after this, many countries in this region, we become more aware of tsunami risk and other earthquakes and other natural disasters. So leading to the idea of early warning system. So this picture shows Siren Tower is a part of the National Disaster Warning Center of Thailand, created after this tsunami disaster. This is another regional warning center, warning about tsunami risk and cyclone and other flood and many other disasters. It's a multi-hazard system. This regional center is located in AIT campus. Some of you may visit in the next few days. So myself and some of my colleagues at AIT have been heavily involved in development of these two regional and national warning systems. Now coming back to this picture, I think if you look at this picture, you will roughly understand which area are seismically active, which area are less active. But if you are an engineer and you want to design your building and structure, this information is not good enough. So we have to convert this into something that we can use for structural design or building design. That is, we call seismic hazard map. Like the one on the right. This is a hazard map created by my research team. It shows ground motion parameter that used as indicator of ground shaking intensity. And this one is a peak ground acceleration for 2,500 year return period. Actually, we create a map for many other return periods, like 500 years and 50-year return period. Okay, we can do that. And this map will give you a very clear idea what are likely to be the extreme ground shaking intensity level, and so that we can design our buildings for such extreme ground shaking. Okay, like this, the north and the western part of the country are likely to have very strong ground shaking intensity, while the other part, the east or the south, have much lower chance. Okay, so you don't have to design building to be that strong. Our team actually work on not just Thailand, but this one is for Thailand, and we can create maps of many kinds. This is a spectral acceleration. For those who are not engineers, maybe not so familiar with this, but we have many types of ground motion parameters to define the effect of ground shaking. Yeah, this spectral acceleration for 0.2 seconds is showing the impact of ground motion to low-rise building, while this one for 1.0 seconds is the ground motion related to the impact to mid-rise to tall buildings. Okay? When we have this type of map or ground motion parameter, we then can create our own national seismic design standard. So that this is our national seismic design standard, incorporating a new seismic hazard map integrate into our seismic code. We use the US code as a model, but we use our own hazard map to replace the ground motion parameter in the US. So we can design our building and structure to be compatible with the safety level as those in the US. Okay, that's the idea. This one is another example. As you have seen the case of Thailand, this is another one. This is in Bangladesh. And this is a whole country of Bangladesh. And different colors show different level of seismic hazard. You can see this scale. If it's yellow or orange or red, it's called high seismic hazard. If it's blue, it's low, but mostly not blue. Okay? Yeah. Our research team has actually carried out this similar seismic hazard assessment for not just Thailand or Bangladesh, but also for other places like Manila City, Malay Peninsula, Sabah Sarawak, and Laos for many hydro power projects, Timor-Leste, and recently for Pakistan. That gives us a more clear idea about seismic hazard in this area and this country. And if you look at the city into this map, you will see right away which city are more exposed to dangerous ground motion. Like, for example, Sylhet is number one. This city is having a very high seismic hazard, while Warintchai is in a much lower seismic hazard. You can compare Dhaka, the capital city, with Chittagong. So for engineers, this information is very critical in the design. So we need that. But for general public, when they see this map, they may not really understand what will be the impact of the earthquake. So I show another type of study that we have made in the past. This is called seismic loss estimation. If we have information about seismic hazard and we combine it with information about geological data like a soil condition, basin, combined with the information about building stock, infrastructure, lifeline, transportation system, if we combine this in the right way, we will be able to estimate the damage or loss created by earthquake for any city or any town or any area. This is called seismic loss estimation. Okay? And we have carried out this one under one program called Comprehensive Disaster Management Program of the government of Bangladesh. We have made it for about more than 9 cities for Bangladesh and more than 10 cities in Thailand. I will show just one example. It's Dhaka, the capital city. The location is here, and we can make a model, not just one building, but the whole city. And this is an example. It shows a map of Dhaka. Show the distribution of the number of building damage, concrete buildings, by a given earthquake scenario. This is an earthquake scenario number 1. But we can have an earthquake number 2 or number 3 or number 10. We can try many possible earthquake scenarios and see what will be the impact. And here, the picture shows the distribution of damage of concrete buildings. We can have a map for masonry buildings, and we can have a map for other type of buildings. This shows the number of casualties, okay, and its distribution. We can then estimate how many people will be seriously injured, how many will need to go to hospital, what will be the number of deaths that will be caused by this earthquake. We can estimate this using this methodology. You can even calculate about medical care facilities. Some of them in the red color means they will not be functional as medical facility. Hospital, we cannot use them. But if it's still in the green color, still functional. Okay? So by this, we can estimate that during the emergency situation right after the earthquake, what will be our capacity to handle this situation. Okay? We can calculate the impact to lifeline, like this one is an example, the potable water system in Dhaka city. Some area, the pipeline will be broken more than others because some area in Dhaka, the soil can be liquefied, turned into liquid, easier than other areas. So this used in the modeling of the city. Well, this type of seismic loss estimation will give you a big picture and an overview, so we can plan for the next earthquake in a more effective way. But the heart of this is we have to understand the vulnerability of our structure. So I'd like to show you that we are not just looking at the big picture, but we are looking at individual buildings. We have to understand how each individual building responds to earthquake. Okay? So, and the problem that we have now at hand is a large number of existing buildings, not only in Bangladesh, but in Thailand, maybe in Philippines, and in Myanmar, and in many countries, are quite vulnerable to earthquake ground motion. Okay? And I show you one example. This we call street front shop house. Okay? The first floor is for commercial activity. The upper floor is for residential purpose. So you can find this type of building almost everywhere in many countries. So, but when you take a close look at it, you will find that it have a concrete frame and with many brick wall, infill wall, many partition brick wall on the upper story because you need a wall on the side and for the interior partitions. You have less number of wall in the first story, especially in the street front. We don't put a wall in the street front so that the people can have access to the building. But we have wall on the side and on the back. So this one creates a so-called soft story in the first story. It creates a torsional irregularity. You have heard about torsional irregularity in earlier presentation. And most of the buildings we have seen so far in many countries, they are not, steel reinforcement are not put in a way that it will make member ductile. So we have non-seismic detailing. Okay, so all this combined together, our buildings are quite vulnerable. So when it's subject to earthquakes, mostly it will deform in the first story, twist like this, okay, and then collapse in the first story. Like the picture I show you here. This is a picture I took after the Tichi earthquake in Taiwan. The first story collapsed. This one is the second story, the first story is here. Okay, and this one also, this one is second story, the first story is also here. Most people who died during this earthquake are those who slept in the first story. So please do not sleep in the first story. Okay? So if you want to survive, stay in the second story. That one too in Nepal, recently in 2015. This is a second story, the first story collapsed. This one, you can see the column incline almost collapsed, but not collapsed yet. This is another one in Kathmandu city. Okay, you cannot see well, but upper story looks fine, but when you take a close look, that's how the column looks like. Almost doesn't look like column anymore. Okay, columns damaged significantly. Cannot carry the vertical load, but it's still standing. And internally, a lot of damage. Yeah, that's how building has been repaired or strengthened after the earthquake. So by the local contractor, they strengthened the column in the first story. I think that's a good solution because that's the most vulnerable part. But there are many other possible solutions, and now our research team are still working on finding many possible options. Because this is a very basic problem. We can find this type of buildings everywhere. Some we can strengthen the front frame, put a wall, or you can change the partition into something more deformable or lighter. There are many other approaches, but I don't have time to explain this in detail. Now let me change the subject. We are not only interested in small buildings, but we are also interested in tall buildings. And one of the research projects we have been working on for many years is about seismic risk in a mega city like Bangkok from distant large earthquake. Earthquake, large size, large magnitude, happen very far away from Bangkok, can produce, may be able to produce disaster. Okay. To understand this, you have to look at the case of Mexico City in 1985. There was a very large earthquake in the ocean, 400 kilometers from Mexico City. But it was able to create the impact to Mexico City. A large number of tall buildings collapsed. More than 10,000 people died because of this one. It's a major disaster, very well known case. When we look at the details, we found that this is a location of earthquake source. The ground shaking was is moderately strong near the source. When you look at the recording station 300 kilometers away, the ground motion intensity becomes weak. And this is Mexico City. On the rock, it looks weak. Okay? Then this green represents a soil basin. On top of the soil basin, ground shaking becomes strong again. It has become, the ground motion becomes amplified by the basin dynamics. Okay? It's become even stronger than this one. And from the plot, you can see that it's turned into what we call long period ground motion. It's a very unique type of ground motion we found only on the deep basin. It's shaped slowly. It takes about 2 seconds to complete one cycle. But it gives a big impact to tall buildings. Not very much on low-rise building or mid-rise building, but much more on tall buildings. Okay, so tall buildings will be more affected by this type of ground motion. We found that these are possible in many basins, in Taipei, in Osaka, in some basins in Singapore, and also in Thailand. Okay? In Thailand, if you look around the whole country, we have a big basin here. The only big basin we have. I may be wrong, but right now our state of knowledge is this, that we have a basin of soft soil here. And this happens to be a location where we have our capital city, Bangkok, where we have many tall buildings. This basin can amplify the long period and create long period ground motion. And we happen to have many tall buildings that sway slowly, having long natural period. So this can create, so the our structure may be quite vulnerable to this type of ground motion. And it's not, we have many warning signs on this. We have earthquakes in China, 2,000 kilometers away from Bangkok. It was able to shake many tall buildings in Bangkok. Earthquakes in Sumatra Island, about more than 1,000 kilometers from Bangkok. Also able to check tall buildings in Bangkok. Okay, so we have this warning. But that's not the type of ground motion we are worried about. We worry about a much larger earthquake at a closer distance, and it might be able to create much stronger ground shaking. So we have conducted a number of research. This is a work by one of my research colleagues, Dr. Nakorn from Thammasat. We conduct what we call array micro tremor measurement. Okay, this is basically putting a sensitive vibration sensor on the surface of the ground. We don't have to dig into the ground to study the soil basin, but we can measure a small level of vibration, natural vibration on the top of the surface. And we can identify the dynamic property of the soil basin. Okay? For example, we can identify the depth to the bedrock. We can check the shear wave velocity profile. These are the basic dynamic properties that we can use to calculate how basin will respond to earthquake, how it can amplify, and how the amplified ground motion will look like. And this is an example how we conduct this. We put the sensor in small array, mid-size array, large array. Conduct this, and we will be able to identify the property. This shows you the Bangkok basin. The dot here shows the location where we conduct array measurement. We have made it more than 100 places over the basin size of more than 100 kilometers wide and 100 kilometers long. So we can calculate the depth to the bedrock. We know that now some part is very deep, close to 1 kilometer. Some parts are quite shallow. So the basin property varies from place to place within this big basin area. We have shear wave velocity profile. This is an important dynamic characteristic of the soil basin. We can make a model, like we make a model for structure, but this is a model for the soil, to calculate how basin respond to earthquake. We can have, from seismic hazard assessment, we can identify what the ground motion will look like, okay, from different source, from different distance. We can have this input ground motion, and then by using our basin model, we can calculate the amplified ground motion on the surface of soil basin. So you can see that this is an input, this is an output on top of basin, so it's amplified. Okay. With this, then you can now put this as input to your structure. Okay, and when you have a model of structure, then we can estimate how our structure will behave under the ground motion. So I'd like to show you another project work that we have done. That is to estimate the potential impact of large descent earthquake on existing tall building in Bangkok. The project is under the Office of Disaster Prevention and Mitigation of Bangkok Metropolitan Administration. They actually want to know what will happen to Bangkok and what they need to be prepared. Okay, so we carry out this project. But they have so many tall buildings there. Buildings with 20 story or higher, we have 1,400. To 20 story or higher is about 600. So which a large building stock that we have in Bangkok. It's a mega cities. So what we did is we collect a drawing of more than 200 tall buildings from DNA. We make a model around 100, more than 100 tall buildings. That's a lot of work. It's non-linear model that you have seen. When we make a model, it allows us to be able to understand how the structure will respond to the ground motion. This is our basic vibration mode. Okay. Once we have a 3D model of the structure, it's not just vibration property, but you can calculate also what will be the damage when the building sway or vibrate in each mode. For example, if the building is damaged in the first mode, if it sway in the first mode, we will see the damage to infill wall throughout the height of the tower, not much in the podium, more on the top and propagate downward to the base. While if we look at the shear wall, concrete wall, the damage will be more like a bending of the wall, create more crack on the tension side. So we can see this impact very clearly when we have a 3D model. Okay? When the structure vibrates in the second mode, you will see the cracking or yielding at different locations compared to the first mode. That's for second mode, this one for the third mode. So you have a different damage distribution for different vibration mode. Okay? But when you apply the real earthquake, it may excite not just the first mode, but also second mode, third mode. So what we see will be a mix of all this. Okay? So you can see this is the result from one example of tall building, showing the damage to many infill wall, partition wall, and damage to reinforced concrete core. Okay? This one is okay, but the other one, this one shows that brick wall, which are non-structural component, will be completely failed. We can no longer use them. We have to remove them and replace by a new one. Okay? Structural wall will crack, but it still remains standing. Okay? And then we check not just these 2 buildings, but 100 buildings. But many of them are not as detailed as like I showed you here. From what we saw, we found that if it's subject to extremely rare earthquake, it's possible that several hundred buildings in Bangkok will be in this condition, where structure still remains standing, but many non-structural walls will be damaged. Many content inside will be damaged. If you cannot understand this, let me show you one example. This is a case in Nepal. Okay, this is a tall building, probably the tallest in Kathmandu, 16 story. Shaken by long period ground motion. This is a type of ground motion we expect to happen in Bangkok. And then when we take a close look, you can see the damage. A serious damage to brick wall. But if you look at the column or the slab, it looks fine to me. Not much damage. So minor damage or no damage to RC frame member. But that's how it looks. Okay? That's how it looks. Right after the earthquake, and then what happened after that is all building occupants were evacuated from this building. It's about 4,000. And they still were not able to go back to use that building until now. Okay, the impact was quite enormous. It raised a question where, if you ask a structural engineer, it looks like we meet the objective. Our structure remains static. Our structure is still safe. but it cannot be used anymore. It has to be repaired. And the downtime produced by this repair process maybe more than 1 year. Okay? So you cannot use a building for a year or maybe 2 years. That will give a serious impact to this one. Okay? So we expect that around several hundred buildings in Bangkok might be like that. I give you another picture. This is for the case of Thailand. This is a tall building collapsed by one earthquake. It's a moderate earthquake located 50 kilometers from the city. In this building, during the earthquake, there were about 327 people in the buildings. About 114 people died because of this one, the building collapse. Fatality rate is about 35%. In the whole city, the number of deaths was 116. So 114 are coming from this single building. And so one building collapse is become a disaster. Okay? If that building is tall building. In our case of Bangkok, we estimate that for different level of earthquake, 2,500 year return period earthquake, we may have about 4 to 70 building collapse. And each building may have 1,000 people in that. Okay? For 500 years, maybe 0 to 4. So if you look into the whole building population, it's just around 1%. But that can create a major disaster. Okay? And together with this, around several hundred buildings will not be functional. Okay? That is a type of impact we can expect by a major event. All right? Yeah, what we can do about this? This is a design spectrum for Bangkok. We are now working on a more accurate design spectrum, account for this basin effect and long period nature of ground motion. That's for new building. But for existing building, we may have to develop a special approach to identify the weak tall building and do something about that. It has not been done yet, but that's something to do in the future. Let me talk about wind. This will be rather short. I will talk more about wind effect tomorrow. We talk about wind effects. I hope I have time. The first thing I like to talk is we have a facility to study about wind effect. That's called wind tunnel. Okay? That's this facility is created by AIT and Thammasat University. So we work together to develop this facility. That's how we can make a small scale down model of our structure put into the wind tunnel, and we can study how it performs. I show you more detail tomorrow about the wind tunnel. That's a project in Vietnam that we have conducted. This is a small model of billboard structure. Okay? The model is about this size, less than 50 centimeters tall, but it represents a structure like this, 30 to 50 meters tall. The structure is huge, and it has a large area. It's exposed to wind load. It's very vulnerable to wind load. And many of them collapse in Bangkok. I think for those who are coming from Vietnam, from Myanmar, you may experience the same thing, even in Philippines. Many billboards collapse during a strong wind. They are quite vulnerable to wind load. So in our study. Oh, my time is over. Is it? Okay, I'm going to run fast. We put the billboard on top of dynamic force sensor. That's called technical high frequency force balance. Another way to study this is to not to measure the force, but to measure pressure directly, with pressure. Okay, that's how it looks. That's a contour of dynamic wind pressure. Okay, the red wind is pushed to the billboard. The blue wind is pulled. It can be pushed or pulled depending on the pressure is higher or lower than atmospheric pressure. So sometimes it's heavy on one side, like this, and then another time it may be uniform. And now it's moved to this side, heavy on this side. Okay, so that's a realistic wind pressure applied to the billboard. Sometimes it's uniform, sometimes it's not uniform. But what is stipulated in the building control regulation is a uniform wind pressure that we use in the design billboard. Okay. In reality, it's non-uniform, and sometimes our drag force, wind force, shifted from the center. In this case, the two columns may share the load half-half. In this one, this single column may carry all the load. Okay, so you can see that if our wind load that we use is not accurate, we may be in trouble. Okay, the building structure may collapse. We can test for many other configurations if we have internal. This also, you cannot find wind load coefficient or wind load information from any code for standing configuration of Buddha statue. It's not possible. So we put it in the model in wind tunnel. We can check the wind force from any different wind angle. Okay. When we combine with our structural model, we have detailed finite element model, combined with a more realistic wind load. Then we can calculate the response in a more accurate way. We can then determine, check the safety of the structure in a reliable manner. Okay, that's the detail made by our team from AT Consulting and Solutions generally. That's a test for tall buildings. But since my time is over, I'm going to explain this more in detail tomorrow. That's maybe better. So leaving me something to talk about tomorrow. We can measure the pressure. We can measure, that's a project in Philippines. We can have a model, we can have a topography around the building. We can check the wind velocity in pedestrian level. Okay. Some area cannot be used for the purpose they be used. I mean, for pedestrian, for putting restaurant, open air restaurant, because in some area it may create what we call jet effect or some local strong wind effect. We can identify this area by internal test, and we can improve that by aerodynamic pressure, aerodynamic measure. This is a dome structure. Okay, that's how the dome looks like. It's a small model, but in reality it's about 86 meter wide dome. Okay, and we can calculate or we can measure wind pressure acting on the surface of the dome. All right. When you have this information from wind tunnel, you can directly use that to calculate the effect onto the structural frame or structural truss. Then you can examine or design the structure in an economic way. The wind load is accurate and the design will be economic. Okay, I think that's the last slide I should talk because my time is over. Thank you very much for your time.